Thank you, Yuji. Thank you for the center for inviting me here. I'm very happy to be part of this center coming through. And this is my first visit. I had a nice tour of the labs and already had some interesting discussions with the chemists. I look forward to having those more. So what I'm going to tell you today is about this new collider. Collider is in high energy physics. Two beams of particles of very high energy, they collide, and we try to look. One of them is a probe, and the other one is the target. Exactly like your microscopes, you want to shine light, and the shining light, when it gets reflected, exactly like any microscope that biologists and chemists use, you look at the reverse light and whatever particles that come out. And from there, you try to look inside and figure out what must have happened inside. The difference between biology and chemistry versus physics is that our wavelengths are much smaller than the optical wavelength. So we cannot actually see as you see in normal telescope or microscope. What we have to do is to look at particles that come out of some collision and then infer what might have happened there, because the distance scales are 10 to the minus 17 centimeters. So that's the difference, but identical, the process is the identical, fundamentally is the same. And I'll try to explain to you what's going on here. So it's the science and the prospect and possibilities at the electron-ion collider. I could have also called this talk Understanding the Gluons, what I call the super God particle that binds us all. And I think there I want to explain to you, I'll go in slightly more detail as to what a gluon is. We know the protons and neutrons. Everyone knows about that. We deal with them as fundamental building blocks of the universe. We as physicists have looked inside the proton to see what they are made up of. And for the last 50 to 70 years, we know that they're made up of quarks. And quarks are particles that so far we haven't seen any substructure to. They're the most fundamental particles that we think so far, scientists think so far are there. But they are bound very tightly together inside the proton using something called the gluons, the glue that binds the quark inside the proton. They're very, very strong force that sits inside the proton, and those are called gluons. And I will come back to a little bit more formal introduction to it later, but that's all you want to know. At the moment, the gluon is called a super God particle. If you remember, in 2012, there was a discovery of Higgs boson at CERN in a collider, much larger collider. And the Higgs boson was important for physics because it was considered to be the explanation for origin of mass. And it was called by some very high-level scientists as God particle. It was known to exist for 50 years, but had not been discovered, finally discovered in 2012. And that's why it was called God particle. And there's a reason why I call the gluons a super God particle. And I hope in my talk today, you will understand why I call it the super God particle. So the quest for fundamental structure of matter is not new. It's old. We know that matter is made up of molecules. The molecules are made up of atoms. The atoms have their nuclei at the center and electrons around them. And if you look into the nuclei, we see protons and neutrons. Protons are the charged particles, neutrons are the neutral particles. And then, as I mentioned to you, we have been able to look inside the proton and discover that they're made up of quarks of different kinds, and they have different colors, and they're bound together by these wiggly little things, which we call the gluons. That's something on screen. So we're curious about it. Where are we coming from? What are they made up of? What is the smallest fundamental structure? These are things that we are all curious about. We want to understand how nature works as scientists. So if that is our nature, how do we know this? Well, we know this because we have used microscopes of different kinds. So here is something that I visited today in your labs, a visual microscope, and this is an electron microscope. What happens in those is that the light is shining with a certain wavelength, and then it gets reflected. That size of the object that you're looking at should be comparable to the wavelength of what we want to use, so that you have a reflection which is then coming out with the appropriate wavelength, and from there you can deduce the structure. So the wavelength here, with the wavelength of 380 to 740 nanometers, you can get resolutions about 200 nanometers. If you increase or decrease the wavelength, that is, increase the energy of the probe, an electron microscope will give you a 0.002 nanometer as wavelength, and then suddenly the resolution starts becoming better. We, in particle physics, do the same thing. What we do, instead of using keV electron beams, we use 20, 30 GeV, giga electron volt electron beams. And then suddenly you have a much smaller wavelength, and you're starting to resolve smaller structures. So that's really what we do. What we essentially try to do is to go from higher and higher energy that goes to lower and lower wavelengths, and that improves our resolution. So typically, when that light hits the target, things come out at very high energy, and we look at that in a detector and then trace back and figure out what happened in the collision. And from that collision, we try to infer what the structure of the target is. Yeah, that is the basic idea. So what do we know so far? So let me introduce you to what we call the standard model of physics. We know that there are 6 types of quarks: up, down, charm, strange, top, and bottom. Those are the fundamental particles. They are unbreakable as far as we know today. They are at the basis of every hadron that you see in nature. Protons, neutrons, lambda particles, you don't have to count, but you can make combinations of these and make all the things that we see in nature. Then there are the neutrinos, which are very mysterious. They are charged 0 and very small mass. We don't quite understand their mass. And then the electron, muon, and tauon. Electron, everyone knows, they are around the nucleus in an atom. The heavier brother of the electron is called the muon, and the heaviest brother of that in that family is called the tauon. Because they are heavy, they like to decay fast. Yeah, they are fundamental particles, but they still decay into lighter particles. Yeah, and so that's the standard model of particles. And then there are these forces. I told you about the gluons. The gluons works inside and interacts amongst these here. They bind all the quarks together inside the proton. We have never seen a single quark outside the proton. That is a fundamental property of the nature of the gluon. It binds the quarks so highly, so tightly together, there is no way to take it out. If you try to push a quark out, on the way out, it will pick up an antiquark and become something called a pion or a kaon or a proton even. It will never see a single quark in nature. We have never seen it. That's now defined to be the property of this force by definition. It's called confinement. Quarks are always confined. The color of anything is 0. Yeah. So that's how it is defined to be. So I'll be focusing on mainly on this quark, this structure today in this talk. Yeah. There have been about 18 Nobel Prizes that are given to this just discovery of this part of the standard model. The light, the electromagnetism that we all know very well, is integrated into this. That is the carrier of force, the photon. Then in the heavy, there are heavy brothers of that photon, which is W and Z, which some of us do experiments at CERN, Shigaki-san, for example, at very, very high energies. The photon becomes massive, and you can study certain aspects of the standard model using that, using W and Zs. And this is the Higgs particle that we just talked about as the God particle that gives mass, which was discovered most recently. I'll focus on that upper part today. So now let's look at a structure of the proton. The proton is made up of 2 U quarks and 1 D quark. Now, why do I say that? The charge of the proton, the U quark, is plus 2/3. And if I have 2 U quarks, it is plus 2/3, plus 2/3. And 1 D quark has a charge of -1. So 2/3 plus 2/3 becomes, and -1/3 becomes 1. That's the charge of the proton. Yes, we know proton is singly charged particle. Now, if I say, what are the properties, other properties of the proton? You all know as biologists and chemists, the proton has a spin. Yes, it has a spin half. We call it a unit of spin is the smallest unit of spin. If you take any hydrogen and push it through a magnetic field, it points to two directions. It can be either this way or that way. And quantum mechanics tells us why that is the case. And that is assigned the property of spin because of that, because it always splits into two, not three, two. If it is three, it is plus 1, 0, and minus 1. But since it becomes only two, we called it spin half and spin minus a half. So proton has that fundamental property. Where can we use it? We put it in the accelerator and accelerate it. We hold it with a magnetic field in a certain direction. We know it is spin half. Absolutely. No question about it. Biologists or medical professionals use that property inside our blood from H2O to make pictures, which are called MRIs, right? Magnetic resonance imaging. That's proton spin half. If proton didn't have spin half, we won't be able to do that. So we know for sure that the proton spin is half. Now, quark spins are also half. So if you're given 3 quarks make the proton, and the proton spin is half, and each one of them is spin half, you can easily make the spin of the proton this way, yes? We have plus 1/2, plus 1/2, minus 1/2. That means what? These 2 quarks are aligned that way, 1 quark is aligned that way, and you get the proton spin half. Very easy. Exactly similarly, you can explain the neutron. Neutron is UDD. This is UUD, this is UDD. And once you have UDD, you have the flip, charge becomes 2/3, minus 1/3, minus 1/3. Charge is 0. Spin can be anything, spin half, and it is spin half. Easy. There is also, as I told you, a 2-quark system that can be formed called pions or kaons. They're actually Golds or Nambu Goldstone bosons. Nambu was a scientist of Japanese origin who got a Nobel Prize for that, understanding the pion structure. So you can actually do that, and you can also explain in a 2-quark system, this is pi plus, spin is 0, plus half, minus half, 0, and the charge is 2/3, and 1/3 becomes 1, and that's why it is pi plus. And very similarly, you can make a pi minus. You can have U bar and D, and then you have a spin of pi minus, the spin is 0, and the charge is minus 1. Very simple. Things work out. Very simple to explain nature, yes? This was the case until about 1989 when I started my career. We did some experiments at CERN, and we completely changed the picture of understanding the protons in a structure. And I'll come back to that. But for now, this is how we think. We thought just 20, 30 years ago that the nature works. Now let's see what the gluon does. I didn't mention gluon in that picture. I told you it binds the quarks, but in that properties of the proton, I didn't mention anything about the gluon. Yes, I didn't mention because I didn't need it, because I didn't appreciate it. Or when I say I, scientists, we did not appreciate the value of gluons until about 1990s. That's when we started discovering everything that is unusual about the gluons. That leads to the origin of mass and the origin of spin, and I'll explain to you what I mean by that. So, the force of nature that deals with the structure of the quarks and the gluons is called quantum chromodynamics, the color dynamics. I mentioned to you before that inside the proton, the charge carrier is the gluon that binds it together, unlike the photon. Photon, what is the charge of the photon? Electric charge? Is it charged at all? Do we know? No, it's 0, right? It's 0 charge. The light that you see here has no charge. It likes to interact with positive and negative particles, but it cannot interact with each other because the other photon it might want to interact is charge 0. So it doesn't know how to interact. But the gluon carries a color charge, 3 types of colors. And that means that the gluon carrying color will be able to interact with another gluon of a different color. Suddenly, you start having a complicated dynamics. Not only will it interact with the quarks, which are inherently charged, but it will also interact with the gluon. And that creates all the interesting aspect of what happens inside the proton. So there are certain very interesting things that happen. It includes the color confinement. I mentioned to you that it is confined. You cannot find a free quark outside. And there is something called asymptotic freedom that these three gentlemen understood based on all the data that we saw by around 2000 or 1970s, 80s. What it means is inside the proton, if you see how the quarks are moving, as long as the distance between them is small, the quarks behave as if they are free gas. There are no forces. So lower the distance, and they're completely free. But if you try to push them apart, like a rubber band, the force increases, and it becomes infinite at a certain point, that it cannot be coming out. You have to do something drastic to break it. And that's what we do in a collider, to break it. But that is all of that is understood in this Nobel Prize winning lecture. So what is the distinction between quantum chromodynamics and quantum electrodynamics? The chromo is color. Quantum electrodynamics is simply charge. The main difference clearly is that the gluons and the photons, the gluons are the strong force carriers, photons are the electromagnetic force carriers. And the difference, as I mentioned to you before, is the gluons carry color charge. The gluons can interact with other gluons. We call it self-interaction, glue interaction. And quarks and antiquarks inside the proton. The photons have no charge. That means they cannot interact with themselves. There is no self-interaction. Self-interactions with the gluons, no self-interactions with the quark. That is the fundamental difference of forces that you see outside the proton and inside the proton. Inside the proton, gluon dominates all the forces. Outside the proton, gluons do not show up at all, and everything is dominated by the electromagnetic force. And this creates all the intricacies. So physicists like to use something called Feynman diagrams to see how these quarks are interacting. So here is a picture of a quark and antiquark that interact with each other and forms a gluon. So this wiggly little thing is a gluon. That's possible in the QCD because these are charged particles, and that is also charged, color charge. So this can happen. On QCD, you can see the gluons can interact like that because each one of them could be a different colored gluon, and you can have an interaction like that. You can have an interaction that looks like that too. Two gluons collide and two gluons come out. It's possible because they have to, as long as the colors are different, they can interact with each other. They can be interacting with each other. In the electromagnetic sector, this is never possible. This is a photon. This is a glue. You see the wiggle different. The wiggle is different. This is a photon, regular light photon. And there you have a quark and antiquark, which are charged, or electron and positron, and they can form a photon. But you can never find three wiggly lines like that interacting here. Not possible. Yeah? That is also not possible. This is not possible. And now you start seeing the complication that will arise. Every time there's a gluon, it can split into two. So you can't tell me, oh, I have one gluon. Never possible. Because that one gluon, as long as it has some energy, it can split into two, as long as the final two states are momentum conserved and energy is smaller. And those two can split into four. The four can split into eight. This can go on forever. So inside the proton, somebody said this morning, there are only three quarks, but they're bound by at least one gluon. But at least that one gluon suddenly starts splitting. If that starts splitting, goes into 2, into 4, 4 into 8, 8 into 12, 16, and just goes on increasing as long as there is finite energy in there. And those gluons can then split into quark-antiquark pairs. So you can have billions of gluons inside the proton and billions of quarks and antiquarks, starting from only 3 quarks to start with, if you think about it. Yes, the 3 valence quark that you were talking about, you start with those 3, they're bound together, but suddenly, as a function of time, you let the proton evolve, and you have billions of them inside, not 3. That's,
so
yeah.
When you have this billions of gluons and many other forms, how do you have a conservation of energy?
It's all confined. There's no finite. A proton is, you can put it in your lab and it's stable. You can measure its total energy. That energy is coming from all the internal aspects of it. As long as you don't give it extra energy, it's fine. It's finite energy, whatever you start with.
But the gluons themselves don't carry energies?
They do, absolutely. In fact, that carries the entire energy of the proton. In fact, that's what I'll show you how that comes out to be. But that really carries 99% of the proton's energy and mass, and hence mass, E is equal to mc squared. So QCD is the correct theory. It has self-interaction term. They must hold the answers to the enormous number in nature's basic questions. What is the origin of the visible mass? How is the mass distributed within the atomic nucleus? What carries the proton's spin? And what can be the degree of freedom to combine to ensure a pion is massless? Pion that I mentioned to you, a two-quark system. Nowhere are there more basic expressions of emergence in nature. Emergence. Emergence is collective behavior without quite understanding where this thing is going. But nature somehow knows the way and produces every proton with exactly the spin half and exactly the mass that we know. That's an amazing thing to think about. There is no one telling it what to do, but nature knows how to build a proton. If I give you 1 billion quarks and gluons, I won't be able to do it. But nature knows, and that's what we are trying to understand. How does nature know that? What is that secret that we are still missing, that we cannot create protons on our own in a controlled way? Self-interactions among gluons is absolutely crucial. So now look at the big picture. Here is a recent result from this Wilkinson microwave anisotropy probe to understand what is the total mass of the universe as it's seen. And that's a gravitational mass, yes? What it finds is visible matter, Higgs mass is this slice right here. This is the visible mass of the universe. This is the dark matter, and that is we think is the dark energy. So the total mass budget, as seen by this probe, is that 70% is dark matter, dark energy, 25% dark matter, 5% visible matter. So what we call visible universe is that 5%. Everything that is made up of protons and neutrons and the atoms is that 5%. We don't know how to deal with the dark sector. This part and this part, we don't even know. That's physics beyond the standard model. We don't know how to deal with it. But we know how to deal with the visible part. So let's deal with the visible part and ask, do we understand the visible part at least? And the answer is no. I'll show you why. Oops. So I mentioned to you this. You know everything about it. We think that only the quark could explain this. But then there is a simple thing that is missing, and that is the mass. If you take the mass of the U quark and a D quark, 3 plus, so UUD is 2 times U is 6 plus 5 is 11 MeV. The rest of it is massless gluons. Massless gluons. The gluons are massless like the photon. But the mass of the proton comes out to be, instead of 11 MeV, 938 MeV. The same with the neutron. You look at UDD, and then you get 2 times 10 plus 13 MeV, but the mass of the neutron is 940 MeV. When the gluons that bind them is 0 mass. There is nothing else. Pions, the same thing, U and D, that's 8 MeV, but this is 139 and this is 139. So the mystery arises as to where is the rest of the mass coming from? And that mass has to come from some activity that goes on inside the proton. Amongst the quarks and the gluon, there is nothing else. That means they're not as stable as as stationary as it's shown in this thing. There must be an interaction. The simplest explanation is the dynamically generated, meaning the energy of the gluons shared with the quarks constantly is creating activity inside the proton. That means that the quarks are not stationary, neither are the gluons. There is some motion. If there is a transverse, so suppose the proton is coming at you, and there is transverse motion of the quarks. That means the proton is coming at you and the quark is moving that way. So let's say a U quark is moving that way. It cannot go forever. It has to turn around because it knows the proton radius. If it knows the proton radius, it has to turn back. And it keeps on doing that. Automatically, you realize that the quark should be moving in an orbital motion. The quark should have an orbital motion. It's only projected transversely on the left and right side. We have done experiments now in which we look for pi pluses and pi minuses when the proton is spinning this way. So you get a proton spinning that way. That means that the quark has an orbital motion this way. It has a projection. And if I hit it very hard and I break it, and a pion is formed. Pi plus is U quark and a D bar quark. Remember in that example there. U quark is the valence quark. And in the experiment, the U quark is moving towards left, say. I find that the pions go to the left, the pi pluses. And the pi minuses which go and they go to the other side. This is experimentally observed now, which tells us there is actual motion of the U and D quarks to left and right, opposite in direction. We know that already for the last 20 years. We have measured them in our experiments at RHIC. Yeah? So we know that there is transverse motion. Transverse motion automatically implies orbital motion. The question is, can we understand it? Can we actually see it? And the electron-ion collider, one of the goals that we see is that. And here is reiterating that. If you add the quark's mass, it comes out to be about 2 × 10⁻26 grams without the glue. But once you put them in a proton, there are gluon interaction that increases the mass by 100 times. And that's the real mass of the proton that comes out. And that's like saying 1 + 1 + 1 is equal to 300. Because the rest of the 297 is coming from that energy. The energy, the E is equal to mc² through the Einstein equation, imparts mass to the proton. And we are trying to understand how that comes about. So here is the experiment we first did to understand the spin of the particle. So that's one mystery that we don't know. Now I'm going to show you what we did in the 1980s and 90s to understand the spin. So we had the electron or muon beam coming through. It spits a photon. Now I'm looking at it as a microscope. And then the photon has to be of a certain wavelength. The wavelength has to be smaller than the size of the proton so that it can go in. And now it shines light on these quarks. And this wavelength has a spin 1. It's a spin 1 particle. And the quark is a spin half particle. So whenever spin 1 particle and a spin half particle interact, the only thing that happens is that the quark flips its spin. Yeah, it is spin half this way, spin 1 that way. Effective spin is that, so it just flips the spin. Now it has two quarks, two U quarks spinning this way. That means if I put 100 of these photons on this proton, then 2/3 of the time, the U quark will flip the spin. And that's what we see. But what happens when it hits this one? It's useless because the U quark is already spinning in this direction of the proton, of the photon. So there is no interaction between them because there's nothing to do. You cannot have a quark with 3 half spin. So that means interpreted this way, it doesn't change anything. So 60% of the time, 66% of the time, the quarks will flip. Now because I can control the proton spin, I did another experiment in which, oops, what happened here? Other way around. I put the proton in a magnetic field which is reverse. So this force now becomes that way. And now suddenly you have 2 quarks spinning that way and 1 that way. And I do the same experiment and I compare results of this versus that. If the carrier of the entire spin of the proton is only the quarks, I can predict what the difference in the cross-section of this and that is. What we found in the experiment that instead of knowing exactly what we expected, getting all exactly what we expected, we found no correlation at all. We found every very small amount of correlation. The difference was much, much smaller than 2/3 minus 1/3. And that told us that this model is wrong. The model that I showed you, the spin are explained by the 3 spins of the quark, was wrong. Where can the rest of the spin be? It had to be in the gluons. So that's when we did the experiments at RHIC, in which we did the same thing, but now with the gluons. At high energy, we started colliding protons and protons. We measured that for the last 20 years, and now we find that even that contributes very small amount of it. And that led us to the idea that there must be a transverse motion of these quarks, which then leads to an orbital angular momentum. So the 3 together, the alignment of quarks, the alignment of gluons, and the orbital motion of quarks and gluons together gives the spin of the proton. So it's much, much complicated than what we initially thought just 30 years ago. So 1975, we thought the proton was like this. Then we started realizing it's more complicated. And now we are going to explore this very, very carefully with a high precision microscope that we call the electron-ion collider. So here is the summary of the spin. We thought the spin was proton looked like this. Now we know that there is lots of glue, and not only that, but there is orbital angular momentum. So the proton spin half is not only the quark spin, but also the gluon spin. That's only about 0.12 out of that, 0.15 out of that. So the remaining part has to be the angular momentum of the quarks and some angular momentum of the gluons. Collectively, the proton is a very complicated object, is what we now understand. And it's an emergent behavior, collective behavior of all these things that come together, but every proton in nature is exactly like that. I will skip this in the interest of, because it's slightly, so I've talked about self-interactions. I've talked about confined motion of quarks and gluons, the transverse motion dependent. We have measured that now, but not to the precision that we want. And then we have to understand if they are actually moving, they always have a spatial distribution. We have completely ignored it so far. We didn't know how to measure it. Now we know how to get to the spatial distribution of quarks and gluons. If you remember your first year physics, orbital angular momentum is radius crossed with the momentum P. R cross P is what we remember from the first year physics. So if you know the radius, meaning the distance from the center of that quark, and its momentum, you know what the orbital angular momentum is. It's R cross P. And that's basically what we are going to do. So the method we are going to use, I want to explain using a watermelon. If I ask you to tell me what is the internal structure of a watermelon, you can do an experiment that looks like this. You can take 2 watermelons, and you can collide them, very high energy, and all the things will fall out. And you can tell me inside the watermelon where the seeds, the red meat, and there is a white border that confines it. That's what you can tell me. And that's what you'll see. And that's what is done at RHIC and LHC right now. Now, if I ask you, tell me the distribution of the seeds in XY direction and YZ direction, you cannot do this experiment. You need a different experiment. And that is that you want to cut the watermelon using a knife. You want to cut it. Knife is unbreakable. Yes? So the probe is the knife, target is the watermelon. In the first experiment, both were probes and targets, and both have structures. So it doesn't work. But with the knife, you can cut it very precisely. I told you the electron or the muon has no structure. And that's when you collide it with a proton, only proton has the structure. If you can control how you can do this experiment, that's what you can do. Then you can tell me what the distribution of seeds was. That's why we need the electron-proton collider or electron-ion collider. We've had ion-ion colliders and proton-proton colliders. We've never had a electron-proton, electron-ion collider. That's what we want to do. So that's one thing that we will go. And it's very easy. The same diagram, the electron comes through, a knife comes through, looks at the proton with a momentum exchange photon, lambda, which is smaller than the size of the proton. That's the, and then you look at it, what comes out, and the electron remains intact. And what you see is simply nice distribution that you want to cut. That's precision that electron scattering brings. I don't want to go into mathematical details, but I want to emphasize one thing. Here is the same diagram that I mentioned to you before. What I'm showing you is that the electron gets scattered, and we can measure that and that in the detector. That's how we bind the detector. We throw hundreds of thousands of electrons at the proton and do the simulation first. And then say, where does the electron go? Then we build the detector, electron detector there. Where does the hadron go? The mess that remains here goes. But what is interesting to me personally is that every time you see that, everything you can figure out first by measuring the scattered angle and the scattered energy of the electron. That's all you need to know to understand what happened inside the collision point. You never ask for anything else. It tells you what is the resolution power, what was the inelasticity of the thing, what was the momentum of that quark that you hit inside the proton as a function of the momentum of the proton. That is called x. That's the momentum fraction of the quark. Everything can be figured out only by measuring the electron scattering. And that's the power of electron scattering, the knife. So let's go further. Just a measurement technicality, but it's very important. So let me show you what we'll do. So what I've told you is the summary of the science. How are the C quarks and the gluons and their spins distributed in space and momentum? Remember, orbital angular momentum requires space and momentum. We have to figure that out. How do the nucleon properties like the mass and the spin emerge from such interactions? So that's about the proton structure. I haven't mentioned it, but in nuclei, here is the nucleus, here is a proton inside, and I shine light exactly like this with an electron, and I hit a quark inside a proton inside a nucleus. And that quark then starts drifting inside the nucleus and interacts with the rest of the nuclear medium. When it comes to the border, as I told you, because of that color confinement property, it will pick up an antiquark. It will never come out alone. It will pick up an antiquark and become a pion or a kaon, and then a two-quark system emerges. And if I want to study how that happens, that is $1 million question. We don't understand how the quark knows to pick up the antiquark to become neutral. And such an experiment has never been done. To study this in a detailed way, you want to study it in different nuclear media. You can change that structure from helium to uranium, and then the quark will interact less or more depending upon the size of the nucleus. You can control that in the experiment. And last but not the least, I told you that the gluons have the ability to split into two, and the 2 into 4, and the 4 into 8 that I mentioned to you before. Inside the proton, they can make extremely crowded gluonic matter. Yes, because it's confined. They're not allowed to leave. That means this process can go, momentum is conserved, energy is conserved. The number of gluons with small momentum is very large. And they're all confined within this proton. And that means that at some point, not only this process happens, but there is a reverse process that starts happening because they are bumping into each other all the time as the crowd becomes large and large. And at some point, current knowledge of QCD tells us that a completely gluonic new form of matter is formed. That's the prediction of QCD right now. And it has some fantastic properties. It is harder than the core of the neutron star. The energy calculations tell us. 100 times harder than the core of the neutron star. We have never seen anything like this. We cannot imagine what that might be. So we need to understand. And so these are the discovery points of the project that we proposed. And then it was evaluated. by an external agency called the National Academy of Sciences, Engineers, and Medicines. And their assessment said that these three goals that we set are extremely important to understand the structure of our matter. We propose some properties of the machine. We don't need to go into details, but luminosity tells me how often, how large a number of collisions can happen. We want a center of mass energy, which is broad. We want polarized beams because we want to understand the spin structure. We have a broad range of nuclei from protons to uranium and two places where we can actually study this. So that's how we defined the project. And then the assessment that came out called the consensus study report that said in very simple words that the science of this is compelling, fundamental, and timely to go forward to build this collider. That's how it happened. This happened in 2018. And since then, we started building the machine as we know it today. So now I want to give you a quiz. What is this? Can you guess what this is? It's a question in resolution, yes. Statue of Liberty, yes? It's very easy to guess, even in the first one. Why? Because you've seen it often. You know that I come from New York. Yes. So it's obvious. As you increase the resolution, more and more people will start seeing Statue of Liberty. Yes. This is because you had the intuition, because you had the prior knowledge, you had the bias of your experience. That's why you called it Statue of Liberty. Yes. In America, it's the students and postdocs and people in the audience know this much faster. More people will say Statue of Liberty than in this case, because your experience is different in Japan, yes? In the US, it is different. So it is based on the experience. Now, I told you, now another, what is this? Cartoon of a man, correct? Person. Only by looking at that on one dimensions, we know it's a man. But you know that the reality is different. A real person looks more like this. And the proton is transitioning from this to this. For the first time, we are respecting the three-dimensional nature of the proton. To say that there is R cross P is a very profound statement. Orbital angular momentum is a very, very profound statement. We are respecting proton in three real dimensions. Now, we have no knowledge of this because never has been this studied very well, which means your intuition will not work this time. You cannot extrapolate just by knowing I am from New York and looking at the pictures that you remember from the Statue of Liberty. You cannot do it, and I'll prove it to you. What is this? We start with the same resolution that I showed you before, but the only difference is you have no knowledge of the internal proton structure in three dimensions, and that's what I'm trying to tell you. What is this picture? Anyone can guess? No. Try again. I improve the resolution. No. I improve the resolution one more time. Still no, right? Anyone can? Anyone?
I was thinking about the Genesis, painting, or gods and
No, 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 no. That would be easy. That would be easy. But here is different. This is Persistence of Memory by Salvador Dali. This is weird. And QCD is weird. Weird because you cannot calculate it. Because you cannot, a theorist cannot calculate it because of the gluon problem. Because every time you say I have 50 gluons, 50 will split into 5,000. And your calculations will not be right. And those 5,000, you do the calculation, and there will be 50,000 the next minute. It's a very slippery object because of that nature of gluon interacting with a gluon, or gluon splitting into another two set of gluons. And that creates all the uncertainty and all the constraints. So this is the example as to why I cannot extrapolate my knowledge in QCD from knowing my one-dimensional proton into a three-dimensional proton. There is no way to interact, to extrapolate. So you have to go and measure it. Fortunately, we know what to do now. So we want to go into 3 dimensions. And formal structure of this now exists. And you don't need to go into detail. The physicist here atomic physicist will also understand this. There is something called the Wigner distribution. There is a momentum, the distance of the quark from the center, and the transverse motion, momentum of this. So this is what we really want. We want the position, we want the momentum, transverse momentum, and what is the linear momentum. Once you know that, you all got everything about that parton, about the quark inside the proton. And then you can do tricks here. You can integrate over things, and we can get impact parameter distribution. We can get transverse momentum distribution. And from there, we can get parton distribution functions, which are very standard in our field. Again, you don't need to know this right now. I'm going to show you in pictures what they look like. So that will be enough physical intuition. But the idea is that the formal structure exists already. So we need to go and measure. We have been measuring this so far. We have to now measure that. We have to measure that, and then get something called the distribution in momentum and position. That's what we want. So let me just show you how we'll do it, because it's easier said than done. First, let's measure the transverse momentum distribution. So here is a cartoon of a 3-dimensional object of a proton. This is the quark. It's sitting at a distance bt and has a transverse distance here and a transverse momentum. Yeah, these are the momenta. So that's what we want to measure. And you can't measure by quark. You have to measure it by many, many thousands of quarks together. So here's what we'll do. So here is the proton. It is spinning that way. It has the quark spinning that way. You see this quark moving that way, orbital motion. If you look at it as it comes to you, it will look like the quark is moving back and forth like a simple harmonic motion. Yes? But I shine light, electron comes through, photon goes through, and it comes out. It hits the quark on the other end of this, and that quark now starts moving out. As it starts moving out, it picks up an anti-quark and becomes a pi plus. I've been saying this many times, but this is a pictorial distribution of this. We have actually measured this. U quarks always come to the left side, no matter what you do. Extra U quarks on the left-hand side. Extra D quarks on the other side. Pi minuses always go the opposite way, which tells you that the U quarks are moving in one direction and the D quarks are moving in the opposite direction. Why? We don't understand yet, but we observe it. There is a 70% of the quarks, U quarks go in one, pi pluses go in the left, and 70% of the D quarks go in the right direction. So once you do this, a simulation of this kind will look like that. That's the ky and kx. And you see 0 is here, and you'll see a 3-dimensional object of momentum distribution based on the very little knowledge we have so far. But we can do a simulation for what it might look like. And that's what a proton might look like. A U quark distribution might look like when we do this experiments in 10 years. Now let's look at what happens to I told you that's the momentum. Now I have to find the position. For position, I have to do a different kind of experiment. If I have a glass bowl, there's water in it, and there are 3 ping pong balls. The 3 ping pong balls are your valence quarks, and the gluon is the water. And you're churning it, so everything is moving inside that glass bowl. If I ask you, go measure the position of those ping pong balls or the momentum of those ping pong balls, you will not take a baseball bat and hit that with the glass bowl, because the glass bowl will split and it will fall and you'll destroy the motion that you're looking at. What you have to do is to take a ping pong bat and slowly go in and see where the position and the momentum is. That's what we want to do in future for this kind of experiment. You cannot break the proton. That means you have to do a non-violent collision. All the things that I mentioned to you so far, the electron hits the proton and breaks the proton. That's a violent collision. In this case, I want to go inside the proton very softly without breaking the proton, deal with the quarks, excite them, play with them, measure them, and then leave without breaking the proton. Can such a measurement be done? We discovered this at Hera in one of my collider experiments, accidentally, that we can actually see this kind of events in the high energy electron-proton collisions. 9% of our events were coming out to be this very special way. So I call them non-violent collisions. And as I grew up in India, non-violence means this, and I now live in the US, non-violence means this. So that's why I call them Gandhian collisions. So what happens in the Gandhian collisions? So I shine light, that goes in, does something here, and a real photon comes out. And I measure that real photon. It only excites the quarks for a while, and the quark de-excites, and that de-excitation gives me a quark, a photon. And the proton remains intact. It just moves a little bit in the direction because the momentum is slightly different. It's very important that I measure the change in the momentum of that proton. A small one, but I have to measure it. Because without that, I won't know that the actual interaction happened. That's the one way. Another way is to look for vector meson. These are two quark systems that come out. And we have also measured them. Again, the proton has to remain intact. What is actually happening, I'm not showing you these blobs, is that this quark inside gets excited by this photon. It emits and falls back into the proton without breaking. A gluon comes out, quark-antiquark pair is formed. This interacts here, goes back in here, vector meson is formed, proton remains intact. We have actually measured this, but not measured this with the precision that we want to distribute, to understand the position distribution of that. But once we do that, and now we know how to do it with the large luminosities, we will be able to tell you the momentum distribution of U quarks and D quarks and position distribution of the C quarks inside. You see, in polarization, in simulations, we can see small differences in where it goes. So we have sensitivity. This is real detector simulation using the information that models that build such things, but we are sensitive to that. And that's why we believe that we'll be able to get both the structure, the position, and the momentum. So to summarize the whole part, I want to summarize, this is what we were doing. I told you that's what we want, but now we are going to do this. This is an MRI of a watermelon. I don't know why you can find MRIs of the watermelon on the internet, but it tells me it's useful because I can now tell you what I'm going to do for the proton. Yes? So that's what we are going to do in the future. Let me speed up. I'll skip this for now unless there is a question. But the last part I want to emphasize is that gluon splitting creates that unusual space of mind. So let's make a thinking experiment. What does the proton look like at low energy? This is my proton, the three quarks that you like, the valence quarks. And this is a time axis. And what are they doing? They are emitting some gluons, they're exchanging. And at some point, I hit the proton and I take a snapshot picture of the proton with the electrons shining. And you ask me, what does a proton look like? I'll call it three quarks and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gluons. So that would be my thought experiment. That's how I will present the paper saying, oh, I looked at the proton, it has three quarks and I have 10 gluons. Now, if I instead go to a collider regime, and this is my way of showing this, this is Lorentz contracted, this is at almost light speed, so the proton is now contracted like this. And if I do this, now what happens? These same gluons are now one property, I don't know whether you know, if you go to light speed, time slows down. You probably know the twin paradox of Einstein, yes? It says anything that you take the light to speed of light, it contracts in that direction, but the time slows down. If time slows down, the gluons have more time to split. The gluons inside now have more time to split. That means the number of gluons will increase more compared to when it was stationary. So at high energy, you suddenly see large number of gluons inside the proton because of that energy that is created. And that's what we want to measure, because that is going to create a very interesting phenomenon. In the Nobel lecture by Frank Wilczek, Origin of Mass, it says that you bring a gluon free of charge, in a free space, and by itself, it will create a thundercloud of gluons. Why? Because it keeps on splitting. It keeps on splitting. It goes to 1 is going to 2, 2 is going to 4. It will go. Come on, go, gluon. Yes, it can keep on going. That can go to infinity. That's what it says in this Nobel lecture. It brings a big thundercloud, a runaway growth to infinity. But it's not true, because you can never find a gluon in isolation. It says isolation. Gluons are always inside the proton. So a picture has to change. You're inside, and suddenly you start doing this. Now that gets very crowded. So now they start doing the opposite interaction. And opposite interaction means that the 2 becomes 1. These 2 will then go further down. So number starts decreasing. So at some point, the increase through such a process and decrease through such a process becomes equal. And at some point, there's a saturation of number of gluons. And it forms something called a condensate. Condensate, they are spin 1 particles, large numbers like atomic condensates. They form a structure which is viscous. It's almost like glassy viscous. So our physicists call them color glass condensate. It's like a liquid glass. It knows if you hit it from here, the wave will travel to the other end of the proton. Yes, you don't need to probe it. It's a collective behavior of all the gluons inside the proton. And that is called the condensate. It has very interesting properties, saturated state of gluons. And that's a discovery that we want to make, that the gluon distribution keeps on increasing, and we have a question. Do they change shape like this? Yeah, this key, that's the number growing because of the growth that I mentioned to you. And the discovery that we would want to see is a unique state of matter in QCD called the color glass condensate. Very interesting properties, which I mentioned to you. I'll skip that and go to the next one to do the realization. Somebody said, how big is your lab or my microscope? So this is a picture from a helicopter. This is our Brookhaven National Lab. And if you come down, let's see here, my office is somewhere there, this building. And this is what you see. It's a 3.8 kilometer ring. All of this exists already. The tunnel exists. We're actually doing collisions as of we talk today in these experimental areas, but the wrong ones. The proton-proton ones are the gold ones, not the one that I'm talking about today. Electron ion are the future. Yeah, that would be locations here, the electron ion collider. So we'll do this in the same tunnel. We'll take out one blue ring here and push in a new electron beam facility. So it will remain the same. The electron beam is the new part that will come in, and we'll do collisions at 2 potentially regions. This is the one that we are now building. Hiroshima is part of it. Riken is part of it. And then in the future, I'd like to see one more experimental collision place come in. And here is a small, so you see the protons or new hadrons start from here. They go in there, go into this collision point. The electrons will start here. They go in the opposite direction. Then they transfer into this yellow. And now we have collisions in these 2 regions here. That's what is going to happen. We go in opposite directions and then collide. And I think what we are doing is electron hitting the nucleus and studying the insides of the proton inside the nuclei. So that's basically how the whole thing will work. There is a large international collaboration that is built around it. We have about 19 US universities, 20 international institutions. The EIC collaboration has been formed with 1,500 people from all over the world. And it's a truly international collaboration. North Americans are only 38%, Europeans are 30%, Asians are 30%. The detector with which we'll measure looks something like this, with contributions from various countries as shown by these labs, by the flags. So this is truly an international collaboration, and We welcome more Japanese to join this effort. This is a timeline. This is 2019, when we started the process of construction project. This is where we are right now, about, forget the names per here, but we are somewhere here right now. And we have about 10 years to go, where this CD4 means our collisions will begin. So that's how long it takes to finish the RHIC program and start this electron-ion collider program. I looked at the WPI mission, and I could not stop showing you this slide. This is a slide that we recently prepared as to what is the impact of the technology that we create on society. It's very important for all of us to think about. There is health and medicine, of course, the radioactive medical isotope, which is for treating cancer, photon sensor for high resolution PET tomography. We are going to be using AI and ML continuously in the design phase all the way to the production phase of the physics. And people who will train the designs, the ideas that will come out of this will be essential, not only in sciences, but even outside, not only in physics, but other physics, but also societies. The accelerator and detectors, we're making testing computer chips, studying proteins, therapeutic drugs, all of that is included. Energy and national security, and creating the workforce, training the next generation of scientists, which is also a very important aspect of the WPI. I thought this, I could not show this. I thought this would be a very, very good combination from the spin physics point of view, from the chirality studies that we will do, and the mission that revolves around globalization, next generation social value for basic research, and leading edge research. So with that, I want to finish with my last two slides. So what we are going to study in the evolution of the universe that we are studying at now with the RHIC and LHC, the structure as to how electroweak physics came through and how protons, how the quark gluon plasma gets formed. And what electron-ion collider starts doing, we take those quarks and start building nuclei and try to understand how the evolution of the universe has happened in nuclei once we start with the protons. And so with that, let me finish. A science of the gluons, what I call a supergluon particle that binds us all. It will help us understand the emergent properties of the protons, mass and spin, and discovery of the high gluon density matter. Along with that, there will be other many, many things that will happen, but this is something that is important. The project has significant momentum now. We have started to build next year, and we will finish construction by 33, 34 and start the physics. It's a very exciting time in high energy physics and nuclear physics. It's really a machine for young scientists. It's something that we are really emphasizing, that this is a machine in which you will take data and interpret it. Thank you very much.